Good morning, everyone. It's great to be here at the Bantalan AI and Sustainability Summit. My name is Vũ Thị Hồng Nhung. I'm from the University of Kitakyushu, and today I will be presenting my study on mangrove forest coverage and its impact on local livelihood in Thanh Hoa Province, Vietnam. Using remote sensing GIS and field survey, this study explores how mangrove change affect both the environment and the local community over the past decades. I'm excited to share how technology can support sustainable management of their vital ecosystem. Let me outline the core object of this study. The first goal is to analyze the spatial and temporal trend in mangrove forest coverage in Thanh Hoa Province from 10 years. By checking the trend, we gain a better understanding of how mangrove forest expanded or degraded over the past decade. The second object to assess the socio-economic impact of their change on the local cultural community. Before diving into specifics of our study, it's important to understand what mangrove forests are and why they matter. Mangrove forests are a group of trees and shrubs that thrive at the interface between land and sea, typically in tropical and subtropical regions. The forests play a crucial role in coastal protection, biodiversity conservation, carbon sequestration, and livelihood support for local communities. My study was conducted in Thanh Hoa Province, located in the northern central coastal region of Vietnam. As you can see in the map, the study area includes four coastal districts: Nga Sơn, Hậu Lộc, Hoàng Hoa, and Nghi Sơn. The districts were related because they have a long coastline and significant mangrove forest distribution. Let me tell you through the methods we used in this study. We adopted a mixed method approach. We combined both remote sensing and GIS with socio-economic survey to provide a comprehensive analysis of mangrove trend. The first, remote sensing and GIS were used to land classification and mangrove cover trend direction. Satellite image allow us to analyze large area over time, providing a clear view of how the mangrove forest has evolved. Next, we conduct socio-economic survey, interviewing local residents to understand how change in mangrove forest impacts their livelihood. For remote sensing and GIS, we use remote sensing and GIS to map our mangrove coverage and detect trend over time. And Figure 2 shows chart of the method used to map mangrove extent and length cover trend. The process being with image selection using Landsat S and 9 images from 2040, 2090, and 2024 year. After selecting the image, we perform pre-processing to improve the image quality, including enhancing resolution and mirroring image band. For classification, we applied the maximum livelihood classification methods. We have a category and land use into specify. To assess the accuracy of their classification, we use coherent kappa which measure the agreement between the classified map and the actual data. This approach allows us to create land cover map for the year 2040, 2090, and 2024, and more importantly, land cover change map that highlight how the mangrove forest area has evolved over the decades. Let's talk about image classification step, which is the backbone of our remote sensing analysis. This step is critical because it helps distinguish between different land use classes, such as mangrove area, mudflats, water area, urban area, aquaculture land, outer forest, and agricultural land. On the left, you can see the process of selecting trending samples, which are used to teach the classification model how to identify various land types. On the right, we can see the classification result. The different colors represent different land use categories, giving us a clear visual representation of where mangrove forests are located and how they have changed over time. After classifying the image, it is critical to ensure the results are accurate. We bring to the accuracy assessment. We use the kappa index to measure how well the classified data agree with actual ground truth data. As shown in the formula here, the kappa coefficient tells us how much agreement exists between the classified map and real-world data. A higher kappa value indicates better accuracy. You can see figure 5, which shows the classified point from satellite image, and figure 6 compares the point with actual Google Earth image, giving us a direct way to validate the classification process. Let's take a close look at how we validate our result by comparing the classified point with high-resolution image from Google Earth Pro. This step is essential for ensuring that our data is not just accurate, but also reliable and now for long-term monitoring and decision-making. This process requires a high level of security and accuracy. You can see classified image with mangrove area highlighted in different colors. About each of the red dots represents a sample point used for validation. Below it, we have a high-resolution satellite image from Google Earth Pro, where the same sample points are measured. By comparing their point with the high-resolution image, we can visually verify the accuracy of the classification. In addition to satellite analysis, I conducted a social survey to understand how local communities perceive and are affected by mangrove forest change. The survey was carried out from 7 to 27 of January 2025 in two selected areas, an expansion site in Hậu Lộc district and a degradation site in Thanh Hoa district. A total of 216 households living near mangrove forest were interviewed. To capture the full rate of impact, we divided the survey into two sections, direct beneficiary and indirect beneficiary. The questionnaire for direct beneficiary, who are households dependent on mangrove pay livelihood. These include activities such as fishing, aquaculture, collecting forest products, or farming or raising animals. We also assess how their households perceive the relationship between mangrove forest and their livelihood. And the indirect beneficiary group are households who benefit from the ecosystem service provided by mangrove forest, such as coastal protection and biodiversity. This survey session aims to understand how the ecosystem service impacts their daily life, even if they are not directly dependent on the mangrove forest. Now I will talk about the result. Let's explore figure 7, which shows land use and land cover trend in 4 districts. We will use satellite image from Landsat 8, 2014 and 2020, and Landsat 9 in 2024. The red area in the map represents mangrove forest. In figure 8, we present the trend in mangrove extent across the 4 study districts. As visualized in the map, the newly expanded mangrove areas are marked in yellow, orange, and red, representing the year 2014, 2019, and 2024 respectively. Look at Table 2, which shows the trend in mangrove forest area across 4 districts in Thanh Hoa Province over the last decade. This data clearly shows how mangrove areas have expanded in some districts, while in others, decline or adaptation remain an issue, particularly in areas where local efforts may need to be intensified. This slide shows information about the respondents in both the expansion site and degradation site. On the left, we can see gender distribution. In the expansion site, most direct groups are male, while indirect groups are mostly female. In the degradation site, the gender radial imbalance across pole group. On the right, we look at the education level. A significant percentage of respondents, particularly in the degradation side, have a non-formal education, about 14.6%. Very few respondents complete college or university, especially among direct groups. Next, let's explore how the community perceives mangrove changes and the impact of debris. In the expansion side, 15% of respondents acknowledge positive mangrove changes, while the remaining 15% are neutral or unaware. However, in the degradation side, only 26% believe that the mangrove have improved, and 74% express concern over negative impact of debris and pollution, which is evident in the photo on the right. The image highlights the severe weight issues affecting mangrove health in the degradation side, further emphasizing the environmental challenges in tow area. Finally, to provide insight into the community perception of waste management in mangrove area. In the expansion side, nearly 15% of respondents rate the waste management effort effective, reflecting a positive community view. However, in the degradation side, 17.9% of respondents view waste management as aberrating or ineffective, showing the significant lack of satisfaction with local waste management efforts. This data emphasizes the need for improved waste management policies, particularly in the degradation area where pollution and debris continue to threaten the health of the mangrove forest. Let's wrap up with the key conclusion from this study. With remote sensing and GIS, this study analyzed mangrove dynamics in Thanh Hoa Province over the past decade, revealing significant spatial and temporal variation. The use of maximum livelihood classification helped us achieve a higher land cover accuracy, particularly in smaller and fragmented areas compared to traditional methods like NDVI. This demonstrates the power of remote sensing in monitoring and assessing mangrove forest over land area and time period. The social survey provided no critical insight into mangrove changes affect local livelihood and social resilience. We found that communities living near mangrove forests are directly impacted by mangrove health and saw varied perception depending on whether their areas are experiencing growth or degradation. Integrating both ecological data and community feedback allow us to support context-specific participatory conservation and enhance that local knowledge and concern are factored into sustainable management practices. Thank you for your attention and welcome any question or feedback.